Hi everyone. Today I will describe powder X-ray diffraction, and it's always called powder XRD. I would consider it as a tremendous expert in solid-state chemistry. My name is Wang, and I'm very pleasure to share with why powder XRD is such an important force. Here is the outline of my talk. I will start with the general introduction of powder XRD, then discuss the basic principle, namely Bragg's law. Next, I will show you the instrument layout, including the major components needed for powder diffraction. After that, I will present two examples that highlight powder XRD's capabilities in identifying phases and monitoring structural changes. Finally, I will show some reference from powder XRD. So for the powder XRD diffraction is one of the most important instruments in solid-state chemistry. It's allowed us to investigate three major aspects of a material: physical phase, inner structural, and crystal type. So what is, for example, the physical phase, is it the crystalline, amorphous, or a mixture? For the inner structural, powder XRD can tell us about lattice parameter, crystal symmetry, and some other informations. And the crystal type, we can distinguish different monophorous, confirm component identities, and detect impurities. Because more real-world samples are in powder or small pieces form, powder XRD is more universally applicable than single crystal diffraction, which require large, perfect crystal. That's why powder XRD has become such a valuable tool in material science, especially in solid-state chemistry and many related fields in other science materials. X-rays have relatively high energy and short wavelengths compared to visible light. This short wavelength is on the order of atomic spacing, which means X-rays can penetrate into the material at an atomic scale. When X-rays interact with the crystal lattice, the diffraction patterns we collect provide crucial structural information. Essentially, by analyzing how the X-rays scatter, we can uncover what's happening inside these materials. The functional theory underlying powder XRD is called Bragg's law, expressing as n lambda equal 2D sine theta. Here, n is an integer, which is diffraction order. Lambda is the wavelength of X-ray. D is the distance between lattice plane, and theta is the angle of index. When this parameter satisfy Bragg's law, which is n lambda equal 2D sine theta, constructive interference occurs and yield a diffraction peak. Every crystalline material has its own fingerprint of peak position and relative intensity. By examining these fingerprints, we can determine an component structure, detect defects, and identify impurities. And here is the instrument layout. A typical lab-based powder XRD setup includes the following components: X-ray tube. This is where X-rays are generated, often using a copper or molybdenum target. Solar slates. This reduces axial divergence, helping create a more parallel beam. Divergent slates. It is used for adjusting the beam width and divergence angle reaching the sample. And the sample is always placed on sample stages, usually as an fine ground powder, and anti-scatter slits, which is used for blocking streaks or scattered X-rays that might come from the sample edges, and beta filter, which is used for filtering out unwanted K-beta radiation, ensuring a more monochromatic beam, mainly in K-alpha. And detector, obviously, it is used for collecting and recording the diffracted X-ray and generating the intensity versus angle data of plot. All these components together produce accurate diffraction pattern that can be analyzed. And this is example one, which is called magnetoplumbite. And here we have an example of refined powder XRD data for 3 different magnetoplumbite compounds. Calcium cobalt oxide, strontium cobalt oxide, and barium cobalt oxide. By applying revealed refinement, we can detect mineral impurity as calcium cobalt 6 oxygen 11 or cobalt 3 oxygen 4 in each cases. In each case, the diffraction patterns revealed which phases are present and in what approximate quantities. Identifying even a small amount of impurity is crucial to understanding the material's property, especially for magnetic or electronic applications. And here is one example. This is the project when I was in undergraduate, and it's antimony doped chromium 4 platinum gallium 17. When we doped this component with variable antimony concentrations, the powder XRD peaks shift slightly, indicating changes in lattice parameter. By tracking the peak position, we confirm whether doping is successful and how it affects the crystal structure. A systematic shift in peak position usually means the interplanar spacing is changing as we substitute different ion. And here is a reference. And for summary, powder XRD is a highly versatile and indispensable tools in solid state chemistry. And thanks for your listening, and thank you very much.